Hello, welcome to Zeta Explained. Today we are going to be examining how close the zeta function can get to 0 when the real part of s is greater than or equal to 1. So the Riemann zeta function is defined as usual as the sum from n equals 1 to infinity of 1 over n to the s, and this sum converges when the real part of s is greater than 1. And as usual, we are going to split out the real and imaginary parts of s as sigma plus it. And in the last video, we showed that the zeta function is unbounded in the region sigma greater than 1 and t greater than some fixed delta greater than 0. And furthermore, we know that when the sigma number is greater than 1, then we know that zeta of s cannot equal 0. So we proved this in episode 5. But now the question today is, can it get arbitrarily close to 0? So it cannot be 0, but can it get very close to 0? And the answer is yes. So we're going to show this theorem today. Theorem 1. 1 over zeta of s is unbounded in the region sigma greater than 1 and t greater than delta greater than 0. And the reason I'm showing it this way, so saying that zeta can get arbitrarily close to 0 is the same thing as saying that 1 over zeta of x is unbounded in some region. And the reason I'm focusing on 1 over zeta of s in this theorem is so that later on we may kind of consider the growth rates of 1 over zeta of s. So usually it's more natural to say that like 1 over zeta of s grows is bounded by some growth rate than to say that the kind of zeta of s approaches 0 as some growth rate. So that's the reason we're kind of phrasing it this way, but it means the same as zeta getting close to 0. And the basic idea of this is that consider a real function f of x equals e to the x, then this function gets arbitrarily close to 0 as x gets arbitrarily negative. And we're going to kind of do the same thing but for a complex function. So to show that zeta of s can get close to 0, we just have to show that the log of the absolute value of zeta of s, which is equal to the real part of the log of zeta of s, can get arbitrarily negative. So the same idea as this. So if we can show that this real part of log of zeta of s can get arbitrarily negative, then we'll show that the theorem. Cool. And just to kind of show the background a little bit more, we already proved that there are no zeros in this green region, real part of s greater than 1. And we also proved that there's no zeros on the red line as well, the real part of s is equal to 1. And we also expanded this slightly back in episode 22 with this kind of zero-free region, the blue line. But we're going to say despite that the function cannot equal 0 in any of these regions, we can say that zeta can get arbitrarily close to 0 in the green region. Okay, so here's how we're going to prove that. We're going to start with the Euler product formula. We discussed this in episode 4 and proved it in episode 4. Zeta of s is equal to the product over prime numbers, p, of 1 over 1 minus p to the minus s. And in the region real part of s greater than 1, this thing converges absolutely, so we may interchange log and infinite product. So log of zeta of s is equal to log of this product. And you probably already know that the log of a kind of at least a finite product is equal to the sum of the logs. But we're saying that because this thing converges absolutely, you can do the same thing for an infinite product. So log of this infinite product is equal to the sum of the logs of the terms. And then log of something is equal to log of 1 divided by something is just equal to negative log of something. And then I'm going to use the Taylor series of log, as I've written down here, to just convert this into another sum. So this thing it's inside, this first sum is now a sum itself, so now it's a double sum. This is just using the Taylor series. Okay, and then we're going to do something to kind of convert it into another form. So we're going to say that the log of zeta of s is a bit too difficult to analyze directly. Like this function is kind of difficult to analyze. So what I'm going to say is I'm going to write another sum, and this sum notably is just the first term of the second infinite product. So the first term, if n is equal to 1, then this thing is just p to the minus s. So I'm going to subtract off all of the first terms. And so therefore, I'm going to say log of zeta of s minus this first term is equal to, this is the definition we have from before. And I'm just taking this first term from the infinite sum, this inner infinite sum, and subtracting it. So therefore, I end up with the inner sum is n equals 2 to infinity instead of n equals 1 to infinity, because this term is just the first term. And then finally, I'm going to use the triangle inequality. So I'm going to move all of the absolute values inside the sum. So therefore, I get a less than or equals. And then I'm going to use another couple of things as well. So 1 over n, so n is at least 2. Then 1 over n is definitely less than 1. And then furthermore, because I'm assuming that the real part of s is greater than 1, then p to the minus n to the s power, then I'm going to say this thing is less than or equal to p to the minus n. And then now I'm going to kind of re-index the sum a little bit. So instead of going from n equals 2 to infinity, I'm going to say n equals 0 to infinity, but I have to factor out a 1 over p squared here to account for the extra 2, like p, 2 powers of p when I change this re-index. Okay, and then if you believe this, then it's almost easier to go backwards for the next step. This is just in geometric series. So 1 over 1 minus 1 over p is just the infinite sum of from n equals 0 to infinity of p to the minus n. Sorry, did I make a mistake here? I think this is just p to the minus 1, not p to the minus n at this point. Or sorry, this is p to the minus n. My bad. I think I'm confusing myself here. Okay, and then we're going to take this thing, and then you're going to say 1 is equal to p over p. So this just becomes p minus 1 over p. And then if you move this p to the numerator, then this p cancels out one of the p squareds here. So you get 1 over p times p minus 1. And then you can kind of write this. So remember, a prime number is an integer. It's not all positive integers, but it's some positive integers that are at least 2. So therefore, this thing is just less than the sum from n equals 2 to infinity of 1 over n times n minus 1, because this is just a subset of this sum. And then finally, this thing is actually exactly equal to 1. But you don't actually need to use the fact that this is exactly equal to 1. You just need the fact that this thing is bounded. Okay, so what we just showed is that log of zeta of s minus this thing is bounded. So to prove that the real part of log of zeta can be arbitrarily negative, we just have to show that the real part of this thing can be arbitrarily negative because the difference of these two sums is quite small. So we'll do this by considering a partial sum up to the nth prime number and then showing that the remainder is small. So we're going to let s equal sigma plus it as usual. And now I'm going to re-index this a little bit again. So instead of saying the real part over all primes of p to the minus s, I'm just going to label each prime as the first prime, the second prime, the third prime, and so forth. So p sub n is going to be the nth prime. And I'm going to say that this is equal to the sum from n equals 1 to infinity of the real part of p sub n to the minus s power. Okay, and then the next step is splitting the s back into sigma plus it. And then for the it part, we're going to use the fact that p sub n is equal to e to the log of p sub n. So that's how we get this term. And then when we take the real part of this, this thing is just a real number, so it stays the same. But the real part of this thing, if you learn about complex numbers, is just the cosine of minus t log p sub n. But cosine is also an even function, so we can get rid of the minus, because cosine of negative times a real number is the same as the cosine of positive times the same real number. And then once we have this, I'm going to split the sum instead of from 1 to infinity. I'm going to split it from 1 to big N and big N plus 1 to infinity. And then I'm going to use the triangle inequality again, or in this case, just saying that because the cosine function is always between -1 and 1, I'm just going to say that this thing is less than or equal to this thing. Because this is the same as multiplying by 1 everywhere, and multiplying by cosine is going to be less than that. Okay, and then once we have this, notice that there's a bunch of these cosine terms here, so we want to use Kronecker's approximation theorem from episode 35 on the sum. And what we want to say is that intuitively we can get all n of these cosines, so this is a finite sum, we can get all capital N of these things to be close to -1 simultaneously. Although this is actually a bit too strong, we can actually just use the fact that they're all kind of sufficiently negative. But to use Kronecker's theorem, we must require that these log of p sub n's, these coefficients in front of the t, to be linearly independent in integers. And fortunately, this is not too hard to prove. Suppose that there were integers, lambda sub 1 through lambda sub n, such that this thing is equal to 0, so lambda sub 1 log of p sub 1, and sum till lambda sub big N of log of p sub big N is equal to 0. And then to show that the linear independence just means that if this is true, then all of the lambdas must be equal to 0. And you've probably seen this before if you've taken a linear algebra class. Cool, so the way we're going to prove this is that if you raise e to the power of both sides, then you'll get this, e to the 0 is 1. And then by the fundamental theorem of arithmetic, or also called the unique factorization theorem, this can only be possible if all of the lambda are equal to 0. And the intuition here is like, let's suppose big N is just equal to 2. So you have 2 prime numbers. So I'm saying, can it be possible that, like, let's say 2 to the 100th power times 3 to the, it has to be negative because we want to equal 1, to like the negative something power. No, I have no idea what this number should be, but like, negative 90th power or something. Can this ever equal 1? And the answer is no, because if you just think about this number, like there's no other, like if you just multiply both sides by 3 to the 90, then you'll get 3 to some power, and then this is impossible. So therefore, it must be the case that if this were some other number like p, so 2 to the capital P power equals 3 to the capital M power, and p and m are both integers, then p and m must be equal to 0. And this is just trivially saying that 1 is equal to 1. Okay, so therefore, all these log of p sub n's are linearly independent, and therefore we may multiply them actually by 1 over 2 pi to get that all of these log of p sub n over 2 pi are also linearly independent. Okay, so now we're going to use Kronecker's approximation theorem from episode 35. And this theorem basically lets you kind of get something very close to integers. So let a sub 1 through a sub n be real numbers that are linearly independent over integers, and then also let b's be some real numbers, and let q be a positive integer. Then there exists a real t in integers x sub 1 through x sub big N, such that this thing is true for all of the little n simultaneously. So if this doesn't make any sense, let's just kind of proceed forward a bit, and then you'll see like what the point of this theorem is, because I think it's hard to explain what the theorem is without actually using it. What I'm going to say is there exists a number t in integers x sub n, such that for all little n equals 1 through big N simultaneously, then t times log of p sub n over 2 pi, so these are the a sub n's that are linearly independent, minus 1/2, which are the b sub n's, minus x sub n is less than or equal to 1/6. So I'm using q equals 6 here. And therefore, if I multiply everything here by 2 pi, I'll cancel out this 2 pi, so t times log of p sub n minus pi minus 2 pi x sub n is less than or equal to pi over 3. Okay, and then the point of all this is that now I can say that there must be a value of t such that for all of the little n equals 1 through big N simultaneously, the cosine of t log p sub n is less than or equal to negative the cosine of pi over 3, and this is going to be equal to negative 1/2. So therefore I can get a bunch of these cosines to all be negative at the same time. And you'll see like why we want this. So what I'm going to say is that the real part of this sum, remember what we're trying to say is that this sum can be arbitrarily negative, and we wrote it in terms of all these cosines here. And I'm saying that by Kronecker's theorem, there must exist a t such that this thing is less than or equal, every single cosine here is is less than or equal to minus 1/2. So I move this minus 1/2 outside of the sum. And therefore, not therefore, but now you can kind of see the point of Kronecker's approximation theorem is that I'm saying that the cosine of something minus 2 pi times an integer, like you can just ignore that. And the cosine of something minus pi is just the negative of the cosine of the thing. So that's why it's like a negative here. With the minus sign here. And then if you continue this kind of line of reasoning, then we know from Euler, I don't think it's really called Euler's theorem or anything because there's probably like a dozen theorems called Euler's theorem, but we know that the sum over all primes of 1 over p, so 1 over prime, diverges to infinity. So therefore, and we covered this a little bit in episode 27, or at least talked about why this is, talked about this equation. We didn't really prove it or anything in that episode about prime numbers. So therefore, for any capital H greater than 0, it's a real number h, there exists a sigma greater than 1 close enough to 1, such that the sum from n equals 1 to infinity of p sub n to the minus sigma is greater than h. And the reason this is true is because if you take sigma to be equal to 1, then this thing actually is divergent, goes to positive infinity. So therefore, if you get very, very close, you must be able to exceed any arbitrarily large value of h. Okay, and then finally, if you fix this sigma, then you can find a big N large enough such that the sum from little n equals 1 to big N of p sub n to the minus sigma power is greater than 3/4 h. because the infinite sum will exceed h, so therefore some finite set of the sums will be greater than 3/4 h. And therefore, or not therefore, but you can also like find at the end also such that the remainder sum, remember there's two parts of the sum, there's a sum from n equals 1 to big N, and there's a sum from big N equals, or big N plus 1 to infinity. So I'm going to say that the second sum is less than 1/4 h. And you can just take n high enough till this is true. Okay, and then therefore, this thing from above, so this thing being less than or equal to this, well, I'm saying that negative 1/2 times 3/4 h is negative 3/8 h, and then this 1/4 h, remember this thing is at most 1/4 h, so this thing is 1/4 h, then negative 3/8 plus 1/4 is equal to negative 1/8. So this whole thing is less than negative 1/8 h. But because h can be arbitrary, therefore real part of log of zeta can be arbitrarily negative. And therefore the zeta function can get arbitrarily close to 0. So that's the proof. Okay, so I'm just going to kind of go over the proof a little bit. So we just proved this theorem that 1 over zeta of s is unbounded in the region sigma greater than 1 and t greater than delta greater than 0. And the proof summary is basically that I'm just going to summarize the steps we had because I know this is kind of technical and it might make more sense to see it all the steps together. To show zeta of s can get arbitrarily close to 0, we just need to show that the log of zeta of s, or the log of the absolute value of zeta of s, which is equal to the real part of the log, can get arbitrarily negative. And the first step is we showed that this thing is bounded by some number. So therefore, to show that this thing is arbitrarily negative, we just need to show that this thing can get arbitrarily negative. And if we split up this sum into two, then we can write one term with a bunch of cosines. And we use Kronecker's approximation theorem to get all of these cosines to be sufficiently negative. And then with some carefulness, we found a sigma close enough to 1 and big N high enough such that this thing is less than negative 1/8 h for any arbitrarily chosen like large h, which then proves the theorem. Okay, so that's our main result for today. And I'm going to go over a couple of extensions. So the first thing we're going to do is use the Phragmén-Lindelöf principle again. So what we did in episode 36 is we did some proof using Phragmén-Lindelöf principle to turn a result. We proved something was true when the sigma is greater than 1, and we used Phragmén-Lindelöf principle to kind of prove a result about sigma equals 1. And we're going to do the same thing here. So the theorem we just proved is theorem 1. It's unbounded, 1 over zeta of s is unbounded in the region sigma greater than 1 and t greater than delta greater than 0. And theorem 2 is the same thing, except I'm switching this sigma greater than 1 to sigma equals 1. And the proof is by this thing called the Phragmén-Lindelöf principle. We showed this in episode 26, although I'm using a slightly altered version of it. Consider a half-infinite strip D, where a sub 1 so a sub 1 and a sub 2 are these bounds of sigma, and then t is greater than or equal to b. And I'm going to say let f of s be some complex analytic function in the strip that is continuous on the boundary of this strip and satisfies this growth condition where it doesn't grow double exponentially. So the function doesn't grow too fast. Then if the absolute value of f of s is bounded by m along the three edges of this half-infinite strip, then the function is also bounded by m everywhere inside the strip. And I'm going to kind of write multiple bullet points at once now. So from episode 5 and 13, we know that zeta of s has no zeros in the region real part of s greater than or equal to 1. So therefore, 1 over zeta of s being an analytic function, and if the reciprocal of the analytic function with no zeros is also analytic here. And I think one thing I actually didn't prove yet is to show that the growth rate of 1 over zeta is not double exponential. I think it actually is a little bit hard to discuss the growth rate of this thing, so I'm not going to prove it this time, but it's definitely less than double exponential. But it's not so easy to prove that that's the case, but you'll have to trust my word that we can use this Phragmén-Lindelöf principle because 1 over zeta of s does not grow double exponentially. Okay, so if you believe me there, then what we're going to say is we're going to analyze the size of this thing along these three strips, the three edges of this strip. So in particular, if you take edge 1 as the kind of right edge, so zeta of 2 plus it, So we're looking at something that looks like this, and I'm looking at the right edge. So this is 2, 1, and then some kind of number here. Then I'm saying on the right edge, then zeta of 2 plus it is at least 0.235, and this is something we proved back in episode 21. Here's the timestamp in the middle of that video where we proved this. And if this is true, then 1 divided by this thing is definitely bounded by some m1 along the entire edge, where it's just the reciprocal of this number. And then for the second edge, I'm going to look at this edge now, this bottom edge. Since this edge is finite and we have a continuous function on a finite interval, then we know that a continuous function on a finite interval is bounded, so this has some bound m sub 2. And then for edge 3, we're now looking at this edge, and we're going to just assume now for contradiction later that this thing is also bounded on this edge. So we don't know if this edge is bounded or not, but let's first assume that it is bounded by some m3. Then you can use the Phragmén-Lindelöf principle to say that this thing, because it's bounded on the 3 edges, therefore this function must be bounded by the max of m1, m2, and m3 for all sigma between 1 and 2. And where did I write it before? I think I left out something, and for all t greater than or equal to b. But this actually contradicts theorem 1, because remember, theorem 1 says that this thing is unbounded in this region. And by using, if we kind of assume that this wasn't true and use Phragmén-Lindelöf, we see that it is bounded in this region. So that's a contradiction. So therefore, we get theorem 2, that this thing must be unbounded on the left line. Okay, so again, this might not make sense, so I'm just going to kind of restate this with a visual. Sorry, so this visual looks kind of weird, but what we're saying is that the red edge here, the red edges are the boundary of this area, and f of s is equal to 1 over zeta of s, and we can show that f of s is bounded on the bottom and the right edges, so this m1 and m2 over here. So this part is definitely bounded, and the contradiction proof is if f of s were also bounded on the left edge, then by the Phragmén-Lindelöf principle, it must also be bounded everywhere inside the strip. But this contradicts theorem 1, which says that f of s is unbounded in the strip. So therefore, it cannot be the case that this function is bounded on the left edge. Okay, so we're basically done with the video, and I will note one problem here if you want to kind of be more precise about this. So in episode 36, we proved a similar result about zeta of s getting arbitrarily large. So not 1 over zeta of s, but just zeta of s directly getting large. And in that episode, we used the thing called Dirichlet's approximation theorem to show not only that it can get arbitrarily large, but also we made a lower bound on how large it gets. So we said as t goes to infinity, then zeta of 1 plus it is omega of log of t. And we actually can't do that for what we showed today. So today we're trying to show that 1 over zeta of s gets arbitrarily large, but you cannot use Dirichlet's approximation theorem, and we had to use Kronecker's approximation theorem. And the reason we had to use this is that for Dirichlet's approximation theorem, you cannot have those offsets, the b's. If you go back to the slide with the Kronecker's approximation theorem, let's see if I can go back, sorry about this. For Dirichlet's approximation theorem, is kind of the same thing, except you don't have the b's. But then if you don't have the b's here, then you're allowed to kind of get a stronger result about the bounds. But in the Kronecker's theorem, we did need the b's, and that's because the reason we need them is because in the thing in episode 36, we just need all the cosines to be close to +1, or at least sufficiently positive. But today what we're trying to do is get all the cosines to be sufficiently negative, and that's why we needed an offset. So therefore, we couldn't use Dirichlet's approximation theorem. We had to use Kronecker's approximation theorem. And this theorem just doesn't give you any bound. It just says a t exists, but it doesn't say like how high this t could be. So therefore, we do not have a result about 1 over zeta of 1 plus it being omega of something. And now, as it turns out, it actually is true that 1 over zeta of 1 plus it is omega of log of t, but the proof is far more difficult than it was in episode 36. And in fact, it's so difficult that I'm not actually going to prove it today or even if I made like the next like 2 or 3 videos about this, I don't think it would be enough to prove this. So I'm not sure if we'll go in that direction next or develop some other theories of the zeta function next, because this is probably not the most interesting thing to prove for a YouTube video. Okay, and then finally, I'm going to give you some visualizations since you sat through 25 minutes of proofs. So remember back in episode 29, we looked at this diagram of the absolute value of zeta of s, and the red line is looking at this thing along the critical strip. So this is now a 3D graph. This edge is the real part sigma, and this is the imaginary part t. So let me redraw this. And what we're saying is that if you set sigma equals 1/2, so you're going along the critical line, then you get these zeros every so often. And these are the non-trivial zeros of the Riemann zeta function. But if you look at the kind of landscape here, or this kind of what this graph looks like, it looks like for a given, how should we say this? Like, it looks like these are kind of ridges. And if the ridges kind of keep going in this direction, right? At least kind of intuitively. So there's no reason you have to restrict to sigma equals 1/2. You could, in theory, like move this line along this direction, and you would still get some ridges, although it wouldn't be quite as strong ridges. And so far, like no one, at least in this strip, like there are definitely no zeros of the zeta function to the right of 1/2. So these will look much more smooth. So it's not going to like bounce here like it does for these zeros. And remember, the function that we looked at today is not the absolute value of zeta, is not zeta of s, but we're looking at 1 over zeta of s. So what we're trying to say is that even to the right of this line, the real part of s greater than or equal to 1, then this function to the right here can get arbitrarily small. And intuitively, it's kind of saying that these zeros at some point later on will have enough kind of pull to make the function very, very small to the right of it as well. And to illustrate that, what we're going to plot is just what this function looks like along one of these lines. So instead of saying sigma equals 1/2, we're going to look at like sigma equals 2 or sigma equals 1 or something like that. And we're actually going to invert it. So instead of looking at 1 over absolute value of zeta, we're going to look at, or sorry, instead of looking at just absolute value of zeta, we're going to look at 1 over absolute value of zeta. And that looks like this. And here are a few chosen sigma bounds. And what we proved today is that if you look at this blue line, sigma equals 1, this blue line goes like this and does this. And at least in this part of the graph where I've drawn, it kind of looks like it's bounded, but we actually proved that this is unbounded. So if you go to like very, very, very large values of t, then this blue graph will exceed any like number that you chose. On the other hand, if sigma is equal to 2, like for sigma if sigma is just any fixed number greater than 1, then the graph is bounded. So if sigma is greater than 2, remember that this thing is bounded by approximately 2.82. And that's approximately like 1 over 0.35 because zeta of 2 plus it is at most, or sorry, is at least like 0.35. But I kind of want to illustrate with this graph is that there's no reason we have to stop at 1. So in a lot of the proofs that we did today in the last few episodes, 1 is kind of a special bound for sigma, and you can't go further to the left of 1. But if you kind of draw this graph, there's no reason you have to like stop at 1. In fact, you can go to negative, or you can go to 0.9 and this graph still looks the same. It just goes up a little bit more. And this is because you're getting closer and closer to these zeros. So if you actually were to approach a 0, this thing would go to infinity. So if you set sigma equals exactly 0.5, then this graph would have a vertical asymptote and then come back down. But I think this is just to illustrate like what we've been showing today. So as sigma gets closer and closer to 1, so if you look at the green graph versus the yellow graph, the green graph is bound by this green bound, but the yellow graph has some bound as well, but it's just significantly higher. And then the blue line is the first one that's unbounded. And then the red line is also unbounded, and it will in fact grow faster than the blue line at truly large values of t. Cool, that's it for today. Thanks for watching.